Okay, hello everybody. Okay, so we're going to continue with the representation of the system, and in this module we're going to look at the general method for obtaining an all-integrator block diagram from the transfer function. And next we're going to look at the state space representation and look at some state space analysis. So let's start with the first topic, with the general method for obtaining the all-integrator block diagram. And let's say we have, for a physical system, we have the differential equation that describes it. So for a given physical system, the system is described by ordinary differential equation, and it is given by y double dot plus y dot minus 2y is equal to u dot minus u. And we're going to assume we have initial conditions that are y of 0 and y dot of 0. Given the input is u of t, given the input u of t for t greater than 0 and the initial conditions, we can always solve this differential equation to get the output y of t. Now what we want to do is we want to get the transfer function. Now to get the transfer function, we know we set the initial conditions to 0 and we take the Laplace transform. So the transfer function can be obtained by taking the Laplace transform of this differential equation. And if we do that, y double dot is going to give me s squared multiplied by y of s. Y dot is going to give me s multiplied by y of s minus 2 multiplied by y of s equal to s multiplied by u of s minus u of s. Of course, notice here the initial conditions are set to 0 to get the transfer function. I can take y of s as a common factor. I'm going to get s squared plus s minus 2 equal to u of s multiplied by s minus 1. And therefore y of s divided by u of s, the transfer function, is equal to s minus 1 divided by s squared plus s minus 2. This is our transfer function, and this describes the input-output relationship of our system. Now we're going to see today that this transfer function does not give us a complete picture of the process dynamics. So this transfer function, the transfer function above, which means this transfer function, does not give us the full picture of the system dynamics. And I don't know if you can guess and know why it does not. If you don't, we're going to come back to it. So for the time being, we'll move on and we'll come back and we'll explain why it does not give us the full picture of the system dynamics. Okay, so for now, we're going to obtain the all-integrator block diagram representation. And to do that, we're going to introduce a new variable that I'm going to call E of s. This is not the error signal, just a signal that we're going to call it E of s. So that when I write y of s, the transfer function, over u of s, which was equal to, it is equal to 1 over s squared plus s minus 2 multiplied by s minus 1. So what I'm going to do is I'm going to take the numerator multiplied by the denominator. So this is y of s over u of s that we got from the previous page. Now what I'm going to do is I'm going to write y of s over u of s as the following. I'm going to introduce e of s, and then this is going to equal e of s over u of s multiplied by y of s divided by e of s. Now if you notice, E of S will cancel, so I'm going to get back my Y of S over U of S. But now what I can do is the following. I'm going to take the transfer function that I split into the denominator part and the numerator part. And what I'm going to say that this part is equal to this part. And then I'm going to say this part here is equal to this part. I can do that. I mean, introduce the new signal E of S. I wrote the transfer function Y of S over U of S in terms of E of S. We did not change anything. And then I split the transfer function and I said, okay, this part, I'm going to call it, it's going to give me E of S over U of S. And the second part is going to give me Y of S over E of S. Okay, so now I can write E of S over U of S as equal to 1 over S squared plus S minus 2. And similarly, I can write Y of S divided by E of S as equal to S minus 1. Okay, so starting with this part here, E of S over U of S, I can write this as S squared E of S plus S multiplied by E of S minus 2 multiplied by E of S equal to U of S. And therefore, I can take the inverse Laplace. This is going to give me S squared is going to give me double dot, the second derivative of E, plus E derivative minus 2 multiplied by E equal to U of t. And similar to the procedure that we discussed before, to get the block diagram, I'm going to take the highest derivative, which is E double dot. I'm going to put it on one side and move all the other terms to the other side. So I can write this as negative E dot plus 2E plus U of t. Now I can come here and can, since I have a second derivative, I'm going to need two integrators. So this is an integrator, and I'm going to have E of t here. This is going to give me E dot, and then I'm going to integrate E dot, and sorry, I'm going to derive E dot is going to give me E double dot. So E double dot goes through the integrator, becomes E dot. Go through another integrator, it will give me E. Now, this equation above tells me that E double dot is equal to U of t. So I'm going to have to add U of t. This is positive. And then I'm going to have minus E dot. So I have to take E dot and feed it with a negative sign. And then it is equal to 2 multiplied by E of t. So I'm going to take E of t, multiply it by 2, and then I'm going to add it, and this is going to be positive because the sign here is positive. So this gives me the signal E of t that I just introduced. But what I'm interested in is the output of this signal, of the output of this system, which is Y of t. And to get Y of t, to obtain Y of t, I'm going to use the second equation that we have here, which is this equation here. So this equation tells me that Y of S divided by E of S is equal to S minus 1. Therefore, Y of S is equal to S multiplied by E of S minus E of S. I can take the inverse Laplace, and this is going to give me Y of t is equal to E dot minus E. And therefore, in order to get the output signal from here, the output, I need to take E dot, and I'm going to subtract from E dot E of t. So therefore, what I can do, I can come here, and I'm going to change the color. I need to add E is going to get multiplied by a negative sign because of the negative sign there. And I'm going to take E dot And if I were to add these together, while E dot is positive and E is negative, this is going to give me y of t. And this is my all integrator block diagram. Now, given this block diagram, so again, when we have a zero in the transfer function, I'm going to do this trick here. I'm going to introduce E of s, and then I'm going to calculate the transfer function to E of s, and then I'm going to write the output in terms of E of s. Okay, so as an exercise, since we are on this, what we're going to do too, let's obtain the state space representation from the system that we just drew. So I'm going to copy this. And I'm going to use it again here with the objective of getting the state space representation. So what we're going to do, we're going to get the state space representation for this system. Similar to what we've done before, let me choose the different color. I'm going to look at each integrator is going to be a state, so therefore I'm going to have a state here that is x1. I'm going to have a second state that is x2. At the input of the integrator is going to be x1 dot. At the input of this integrator is going to be x2 dot. So therefore I have two states, x1 and x2, two integrators, and therefore second order system. Now looking at this, I can immediately tell that x1 dot is equal to x2. x1 dot is here at the input of this integrator. And x2 dot is equal to negative x2 plus 2 multiplied by x1. And therefore, and also I have u of t plus u of t. So I can write these in a matrix form, and to write in matrix form I have x1 dot, x2 dot, and these are gonna equal to 0, 1, 2, negative 1 multiplied by x1, x2 plus 0, 1 multiplied by u of t. Now I'm not sure you know how fresh you are on algebra, but please try to review. I mean, hopefully with some practice this becomes very clear. x1 dot is equal, if I multiply 0, 1 with x1, x2, the 0 is going to multiply x1, 1 is going to multiply x2, is going to give me the first equation, and 0 is going to multiply u of t. The second equation, x2 dot, 2 is going to multiply x1, so it's going to give me this term. Negative 1 is going to multiply x2, is going to give me this term. And then 1 is going to multiply u of t, and that is going to give me x2 dot. Now also, I want to mention, when we write the state space representation, we always, I mean, if somebody is looking and say, okay, why did you do it this way? Always we write the states derivative on the left side, and we write them in terms of the states. So the format is that I'm gonna have the derivative of the states in terms of the states and in terms of the input. And that's why x1 dot, I need to write it in terms of either x1 or x2. And from the graph here, x1 dot is equal to x2. x2 dot, I need to write it in terms of x2 and x1, and in terms of the input. I hope this is clear, but nevertheless we will be seeing it and it become clear. Okay, so next I'm gonna write the equation for the output, y of t, and again the same thing, y of t, I'm gonna write it in terms of the state. Y of t is equal to, it is equal to x1 or negative x1 plus x1 dot, but I should not write it in terms of x1 dot, I should write it in terms of x2. I hope this is clear. So y of t, I'm going to write it as negative x1 because I have this minus sign here, and I'm going to have to add to this x2. x2 is this signal here, which is the same as x1 dot. Now, could I have written y of t as equal to negative x1 plus x1 dot? I could, but I will not be able to get the state space representation. If I am writing the state space representation on the right side, it has to be the states without the dots. Okay, so therefore I can then write y of t as equal to negative 1 multiplied by x1 multiplied and x2. Y of t is going to equal negative 1 multiplied by x1 plus positive 1 multiplied by x2. And this is our state space representation. Okay, now let's look at make some observations here. So the first observation is that the ordinary differential equation that we had in this example describes a system that is of second order. Second order system. And therefore, all the integrator block diagram requires two integrators. This is not random because it's second order. We're going to require two integrators. And also, the other observation is that the state space representation involves two state variables. The state space representation, or model, involves two state variables. So you see the relationship. Second order, we need two integrators. The state space representation is gonna have two states. Okay, so now I'm gonna go back to the question that we asked here, which is, we said this transfer function is not giving me the full picture of what's happening in my system. Why? Let's go back and look at the transfer function. So go back to transfer function. And my transfer function was y of s over u of s is equal to s minus 1 divided by s squared plus s minus 2. Now, the first thing that is going to come probably to many of yours mind is that let me write the second order equation in the denominator in terms of its roots. So I can write this as s minus 1 multiplied by s plus 2. And if I do that, I'm going to notice that I have a 0 and a pole that's going to cancel each other. This and this are going to cancel each other. So therefore, I'm going to have 1 over s plus 2, which is a first order. This is a first order system. So therefore, due to the pole 0 cancellation, the transfer function does not provide us with a complete description of the system. So if I am deriving the transfer function for this system, what am I going to do? I took differential equation, model, simplify. I then simplify s minus 1 with s minus 1, cancel out. I end up with 1 over s plus 2. 1 over s plus 2 tells me this is a first order system. But in reality, the system, the dynamics of the system is that of a second order. So here, because we have pole zero cancellation. The transfer function representation does not provide a complete description of the system. And in this example in particular, if I apply an bounded input to this system, then the output is going to be bounded, y of t, since y of s over u of s has a stable pole. However, what I'm gonna observe here is that inside this system, somewhere inside the system, there is going to be a variable that is going to grow exponentially. So again, let me repeat that. So if I look at this system, so this is the transfer function that we just simplified, and we said we can simplify it as 1 over s plus 2. If I come here and apply a bounded input, so I'm going to look at bounded input, bounded output stability. If I apply a bounded input, the output is going to be also bounded. So somebody is going to look at this system, tell me, yes, 1 over s plus 2, this is a bounded system, isn't it? It's a stable system. The pole is in the left half plane. We have a single pole. However, if I come to this system, I mean, imagine this is a circuit, or this is any system that we're trying to model. Inside this circuit, inside this system, there is an unstable pole, which was at s minus 1. So somehow inside this system, there is a signal that is growing exponentially. I hope this makes sense. Okay, so for this system, a bounded input u of t will produce a bounded output y of t. And again, this is true since the transfer function between the input and the output is just 1 over s plus 2. However, the internal state variable or variables are growing exponentially. Does that make sense? So again, because we have a pole zero cancellation, the transfer function does not tell me anything about the pole zero cancellation. However, if I look at the state space representation, this state space representation will give me the internal states of the system. So I can, if I were to analyze this system using state space representation, I can plot each one of these states. I can plot x1 and plot x2 in addition to plotting the output. And then it will show me that there is a state that is unbounded, that is unstable. Does that make sense? And this is one of the main advantages of the state space representation. And in that advantage is that it gives me a complete representation of the system dynamics. Not only what's happening at the output, but it also tells me what's happening inside my system. Make sense? Inside the system. If I'm building a circuit, I might build a circuit or design a circuit and tell you overall the transfer function of this circuit is a stable system. If you apply a stable input or bounded input, you're going to get a bounded output. However, if you take this circuit and use the state space representation, you might find out that you have some states that are unstable, and therefore they might be growing to infinity inside the system, but somehow get multiplied by something that's going to 0, and therefore is not showing at the output. And this is what happened in this example. We have a pole here that is unstable, which is the S-1. So somewhere inside this circuit or this system, there is unstable pole that is going to cause this signal to go unstable. But because it gets cancelled by the 0 on the output, you will not see it. But inside the system, you will see it. So again, this is the main advantage of the state space representation. So advantage of state space representation. And I'm going to list it here, is that it provides a complete representation of the system dynamics. Okay, so therefore, I mean, when we are designing using state space representation, not only we are looking at the output and we're looking at the input, we're going to be also looking at the states to make sure the states are stable. The states are not exceeding a certain limit. Okay. So let's go back to the state space representation. And again, in this course, we're going to be using the state space representation throughout the course. Unlike the control systems, the linear control class, where we just introduce the state space at the end, here we're going to be using it throughout the course. Okay. So again, the main advantage of the state space representation, or the advantages of the state space representation, in addition to what we listed above, are the following. First, it allows for linear algebra to be used in the design of the control system. So one advantage is allows powerful tools from linear algebra to be used in the control design. And we'll see some of these tools in the coming modules. Another advantage of the state space representation is we can use it to represent multiple input and multiple output plans or systems. Okay, we have not seen this and we did not give an example, but we could have a system that has multiple outputs. And I can use the state space representation. If I'm using the state space representation, I can represent all the outputs, and by the same token, if I have multiple inputs, all the inputs in one state space representation. If I were to use a transfer function, then I'm going to use a different transfer function between each input and each output. With the state space representation, the output y, when we have the representation here, y, this could be also a vector. So here we have a single output, so therefore we have one output we have y of t. This y of t can be a vector, y1, y2, y3, as many as we have outputs. Similarly, u of t, in this case we have a single input. If we have multiple inputs, we could have y1, u1, u2, u3, as many as we have inputs. So therefore, we can represent a system that has multiple input, multiple outputs in one representation. And the third advantage is the one we just mentioned above, which is it provides a complete internal model of the plant. Okay. So from now on, from this module on, we're going to be focusing on the state space representation. So we're going to focus on the state space representation. We learned in the previous modules how to go from one representation to the other. Now the state space representation will be the focus of our modules. So again, going back to what is a state, a formal definition. The state of a system is the minimum number or the minimum set of variables, and you can represent it x1, x2 of t, etc., all the way to xn of t, that are required to completely describe the dynamic of the system. x1 all the way to xn, that are required to completely describe the dynamics of the system. Okay. Now these n variables are referred to as the state variables. So state variables are the x1 of t, x2 of t, all the way to xn of t. These are referred to as the state variables. And together they form an n-dimensional vector state, n-dimensional state vector. So together they form n-dimensional state vector. So therefore we have x of t equal to x1 of t, x2 of t, all the way to xn of t. Okay. Now when we have a linear, if we have a linear nth order ordinary differential equation with constant coefficients, so it is time invariant, can always be represented as a set of first order ordinary differential equations. So given any nth order differential equation, I can always write it in terms of a set of first order ordinary differential equation, and the representation that we do it is x1 dot, x2 dot, all the way to xn dot equal to a multiplied by x1, x2, all the way to xn, plus b multiplied by u1, u2, um. Now this again is the state vector, and this is our input vector. And of course, notice here I'm using n and I'm using m. M and n are different. M is by how many inputs we have. If I have a single input, I'm going to have only u1. N is the number of the states of the system. So if it's an fifth order differential equation, n is equal to 5. I could have a fifth order system that has one input. It can have two inputs, three inputs. So the m refers to the number of the inputs. So again, n is the state variables, the number of state variables, and m is the number of inputs. And therefore, the A matrix is going to be an n by n, because it relates the n derivatives to the n states. And the B matrix is going to be an n by m. So if I have a single input, then it's going to be n by 1. If I have two inputs, it's going to be n by 2. I hope this makes sense. Again, we're going to be seeing it throughout and becomes hopefully more clear as we see more examples and more of the state space representation. Now, one thing I want to say before I end this module is that in these examples, we derive the state space representation from a transfer function or from a differential equation. However, in general, if I have a system I'm trying to model it, I can just model it directly from the system itself. I don't have to generate a transfer function or generate the differential equations to get the state space representation. I can directly work with the system and define the states of the system directly from the circuit or from the physical system. I hope this makes sense. If we need, I can put an example that we've done where we have a circuit and we try to get the state space representation from the circuit by looking at the voltage, for instance, at the output of the integrator, and say we're going to define this as a state, the output of a capacitor, this is another state, and then try to relate these voltages in terms of the currents and the voltages in the circuit. So again, I don't need to get a transfer function in order to get the state space representation. I can work directly with the circuit or with the system I'm trying to describe to get the state space representation. And maybe I will add to these notes before I post them, I will add an example and you can look at it just to see how this is done. Sounds good. I'll stop here and we'll continue with the next module focusing on the state space approach to the control system. Thank you, everybody.